This is the second session of the Basic Solid-Liquid Separation course. In this session, we will discuss basic and simple principles for solid-liquid separation technologies. These are just for you to get a feel of what are involved in solid-liquid separation, and we will not go into details. As we have discussed in the previous session, solids-liquid separation can be divided into filtration and separation depending on if a filter medium is used or not. There are 4 different types of filtration. They are straining, cake filtration, depth filtration, and membrane filtration. We will discuss each mechanism and its key principles in this session. The so-called separation is achieved by some kind of field forces. We will focus on separations by gravity field and centrifugal field in this course. This page shows different filtration mechanisms. In A, the mechanism of straining is shown. It is simple. When a suspension is passing through a screen, particles larger than the screen opening are retained and particles smaller than screen opening can pass. This is the simplest and the commonly perceived filtration process. When there are more particles in a slurry as shown in B, the particles retained by the screen will accumulate and form a particle bed called a filter cake. This is a cake filtration process. The filter cake still allows liquid to pass through but catches small particles. It even catches small particles which can pass through the screen. The filter cake becomes the actual filter medium, and a cake filtration process can catch particles much smaller than the screen opening if the particle concentration is high enough. Instead of particles being caught on the surface of the filter medium, if particles are caught inside the filter medium as shown in C, it is called depth filtration. This type of filter is normally used for suspensions with very low particle concentrations, say less than 100 ppm. They serve as clarification filters. Membrane filters description is written on next page 2-4. This page iterates the 4 filtration mechanisms we just discussed. Membrane filters are used to catch very fine particles which form very high flow resistant cakes. To prevent this high resistant cake from forming, a technique called crossflow as shown in D is used. With sufficient shear generated by the crossflow, a cake cannot be formed and a decent flow rate through the filter can be maintained. This kind of filtration mechanism was developed due to the rise of membrane filtration. We need to know that with crossflow, dry solids product is not possible as it needs to remain flowable. Depending on the material, 5-10 Wt% are about the maximum solid concentration a crossflow filter can achieve. The 4 filtration mechanisms are also categorized into either surface filtration or depth filtration. In surface filtration, particles are retained to the surface of the filter media. This group includes straining, cake filtration, and crossflow filtration. In depth filtration, particles are caught inside the filter media. This term is the same as the one we introduced before. The filtration can also be considered as either dead-end filtration or crossflow filtration. In dead-end filtration, the flow direction is in perpendicular with the filter medium surface. This group includes straining, cake filtration, and depth filtration. In crossflow filtration, the flow direction is in parallel to the filter medium surface. It is the same as the crossflow filtration we introduced earlier. Now we will discuss a little more on each individual mechanism. Straining is the simplest one and is quite straightforward. The particles larger than the screen opening got retained and particles smaller than the media opening can pass. In the equipment session of this course, we will discuss about some straining equipment and their operations. In cake filtration, particles are retained by the filter medium and the accumulation of particles forms a cake. After the cake is formed, the cake becomes the primary filtration medium. Finer particles can be caught. Driving force for filtration can be gravity, vacuum, hydraulic pressure, or mechanical pressure. Resistances to flow come from both filter medium and cake. As the cake grows thicker, the resistance also becomes higher. A typical filtration curve is shown on this slide. The particles form a porous structure called cake and liquid flows through the cake. Therefore, The principle of flow through porous media can be used to describe the cake filtration process. Darcy's law is the basic for all flow through porous media. It is shown in equation 2-1. It states that the pressure drop over a filter cake is proportional to the liquid viscosity, the term filtration flow rate Q, and inversely proportional to cake permeability, K. The equation can also be expressed with the resistance term, but the formula becomes a little more complicated. Both resistance and permeability are used in this field, but we will only use permeability for this course for simplicity. The Darcy's equation can be integrated to get the filtration equation as shown in equation 2-2. This equation is quite helpful for the understanding of a cake filtration process. It says filtration rate Q can be increased by increasing operation pressure P, cake permeability K, or the reduction of liquid viscosity micro. On the other hand, the filtration rate is decreased if the cake becomes thicker, that is L increases, or medium resistance becomes larger. The medium resistance can increase if a tighter filter medium is used or the filter medium becomes partially plugged. We can see from equation 2-2 the impact of liquid viscosity as we discussed earlier. The filtration rate is inversely proportional to the liquid viscosity. New development has allowed more precise prediction of cake filtration behavior, but the formula tend to be complicated and require computer solutions. Equation 2-2 remains a simple but effective correlation for practical applications. It is also called the conventional filtration equation to distinguish from the newer development.